share with you the musings and the information that I've gathered over the last 3 years. I also want to give a big acknowledgement to the partners at the university who works with people working on water saving and general minimization of water. But most of these ideas that I'm going to share today are either my own thoughts, stuff that I've researched for my PhD, some collective wisdom in the industry, and I'm sure that you'll be able to figure out the difference between my musings and the facts that we're going to see in the talk that I'm about to give. I'm going to dwell a little bit on not only the technology that we use in the tanneries, but also the technology that you'll get in the general industry that supports the technology of the actual tannery. And you're going to come on to those a little bit later. I have three parts to this talk. First of all, I want to talk about the water use that the tannery actually does, a little bit of the history, the properties of the water that we use, the history of water use in tanning in general. I want to have a look at the environmental impact that the leather industry has in general and how it's perceived, what we can do to change these things, how we can improve our measurements. I also want to then have a look at the technology specifically, and I'm going to dwell on drums. I'm going to look at drums. Part of my work for my PhD. So as an introduction, the leather industry has always been described as an intensive user of water. And everybody comes back to the textile industry, and the leather industry has been extremely high user of water. It's often related to shock headlines. Everybody wants to talk about pollution, and they find the worst possible picture that they can, and then they say, look, this is the tanning industry. We all know this is not generalized. This is a generalization of the industry, which is not specific enough. Earlier, Mike was talking about European tanneries achieving excellent ratings. And we need to highlight these things more. Of course, it's a universal solvent. It allows us to dissolve all kinds of things. And because of its properties and its abundance and its cost, it just seems to be a natural thing that we use. So let's have a look at some of the properties that water has and why it's just naturally found a home in the tanning process. Of course, it's a polar solvent. It interacts very easily with ions, ionic solutes, polar solutes, and don't forget that the majority of our chemistry has been built with the idea that we're going to be using water as a solvent. It has excellent hydraulic properties, which is why it's used in water cutting. It's very resistant to compaction. When it's inside the drum, this will be useful. I'll come on to that a little bit later. Its thermal properties are quite unique. It takes a long time to heat up, but once it's heated up, it insulates the heat that it gains pretty well, doesn't lose it very easily. And so again, in tanning, where we often vary the temperatures, it's going to be useful. Of course, when it's in our biomaterial, it's going to act as a plasticizer, and this is it's going to give us the flexibility that we have in the final product. Any of you over-dried your leathers will know it's brittle and hard, not very useful. And so again, it's vital for our product. The surface tension is an interesting one because at times it gives us problems. It doesn't want to penetrate into the leather. Other times, because it sticks to the leather, it's useful. It allows exchange of material. Because it's adhering, you can have the materials flowing away from the leather surface, and as a result, there's no interaction with the chemicals that contain the solvent. Of course, it's a weak bond sometimes, and this can be exploited. We can add soaps, other chemicals which can change the surface tension, and so we've learned to manipulate its surface tension. Even in the finishing, we heard about flow out today, Fujifilm. They'll be able to flow out and give us films. These are all parts of water in the process. The tanning history with water, we know that going back in time, we've used pits, we've used tanks, we've used barrels. These would often be recycled. And then we started to take the water and put them into tanning drums and turn them, change the whole nature of how much water we actually use. It's not unusual for us to use pits, drums, processes, unique equipment, and all these kinds of vessels are used across the world and have different water use. Leather is either partially or wholly submitted in the solutions, and this can have massive impact on the properties and the types of penetrations or extractions that we get. Of course, when the water is in the drum with the material, the flexibility of the flexibility of using it, the types of chemicals that we can put into it, the fact that we can put fats into water even though they don't want to be there, the dispersions that we make, protein dispersions or pigment dispersions. These are all things that we can do with water to get them to be involved in the kind of chemistries that we use. Now, the water legislation that's impacted both the UK industry, the European industry, the global industry, I'm just going to give the UK legislation that had the biggest impact. I'm glad Dave's walked back in the room because he'll remember this one. In 1875, the Public Health Act allowed tanneries for the first time to move away from the watercourses. So in Northampton, for example, the sewage system and the building of the Billinghappadrome sewage works has meant that tanneries were able to move to Wellingborough, Desborough, Irthingborough, Rushden. All these places allowed tanneries to move away from the water sources. So this legislation, the fact that tanneries and towns were forced to have sewage works, was very instrumental. And of course we have the Water Act in 1973, which was superseded in 1989. This, for the first time, started to restrict what substances you could put into the water and what levels you could use. A little bit later came the Industry Act, the Water Industry Act. This gave the government more instruments to prosecute people who were polluting water sources. And for the first time, tanneries would charge not only on the pollutants, but how much water they were actually producing as well. Because up until that stage, everybody knew that the solution to pollution was dilution. At the moment, how much water do we use? Of course, it varies from what type of material we're processing. If you're processing woolen material, using extremely large quantities of water. Sensitive, exotic materials, materials that could tear in the drum, not in the drum, you will tend to increase the amount of water that you use. And so your water usage could be as high as 50 cubic meters per ton of material. Some tanneries will be able to say that they can get their water usage down to as low as 7 cubic meters. With technology like low floats, pit processing, combination, recycling, all these kinds of things could help you get down to that particular level. And so if you listen to people talking about water footprint, which I'm going to talk in a second, you'll hear people say that your cup of coffee that you had this morning was actually 18 litres to make it. Okay, 18 litres, not just the 250 mils, but the 18 litres in the whole footprint, which I'll talk to you in a second. And if you take into consideration that the 7,000 litres of water that you need per tonne there, that's 7 litres per kilogram. Now, it's not going to be as simple as that, because I'm going to show you in a second that we not just want to be interested in the consumption of water, but also the other things that are going to consume water in your process. Yakov and Ivan, they've had a look at this, and the latest figures that we teach our third-year students, you could be looking at about 25 cubic meters as the average in our industry. The Water Footprint Network quotes 16,000 litres per tonne of material. I like the 25,000 litres per tonne of material, because I think it takes into consideration some of the other tanneries that might not be as water efficient as possible. Okay, so let's get on to the concept of water footprint. First of all, why would you want to do water footprinting? Why measure something? Why do we want to draw attention to these things? Well, as most of you know in quality control, if you can't measure it, you're not going to be able to control it. And so organizations since 2002, research groups like Holland, Hoekstra, which I mentioned in the abstract, Allen, 2002, these organizations for the first time started to lay down the framework of measuring water footprint. So just like the carbon footprint, a way in which you're calculating your economic impact or your water environmental impact. The water impact is a sum of two things. First of all, your direct consumption. You put a meter on your pipe, you detect how much water goes through that pipe, you know how much you're consuming. But they found that to be simplistic, and they couldn't understand when they did water footprints in countries that are very water scarce. Why were these countries still seeming to lose water? What was happening? Because the water consumption wasn't good enough. there was still water being taken away. And so the ISO method, which I'm going to come on to in a second, started to highlight that you needed to do something called the virtual water footprint. I'll come on to that in a second. Okay, so there's the ISO 1446 method. So you would just go along and you would calculate exactly how to do this water footprint. It looks at two things. First of all, the direct use and the virtual footprint that I mentioned. The direct use looks at types of water, the blue water, which is the water in rivers, dams, reservoirs, the stuff that you've seen tap in. It looks at the green water, which is the water in the soil. It also looks at the water captured in plants. And then, of course, it looks at the grey water, the stuff that you shove down your bathtub every day. And these waters are used in calculating all of the numbers that you get. And as I mentioned in the slide before, it can be used on a national scale, it can be used on an individual scale, it can be used on a company scale, it can be used on a global scale. It's a very useful tool. And of course, there's databases full of these numbers for different industries as well. Now, the water that we do have to think about is, of course, the indirect water use. Where is these extra liters that we can't seem to account for going? I'm just going to alt-tab out here, show you another slide, which I think will help to explain this. This is another slide taken from the Water Footprint Network, Hoekstra 2016, so this is this year's data. And what you'll be able to see is you'll be able to see areas where there is an incredible amount of water shortage. So this is months of the year where there's scarcity of water, and you can see the western seaboard of the US, parts of Mexico, Argentina, South Africa, parts of India, especially the western, Pakistan, even Vietnam, Cambodia. These parts over here show water scarcity certain times of the year. Now, what is interesting is that we have direct water consumption by companies. We also have indirect water consumption. Now, what do we mean? It means that when you produce electricity, when you produce products that are going to be used in another industry, you are exporting some of the water footprints to that particular country. So if you have countries that are particularly stressed for water, why give them manufacturing where it's going to stress their water resources even further? So for example, when you generate the electricity required to spray dry your powders that you're going to be using in your processing, that water cost has to be accounted for somewhere in the equation. So if the spray drying is done in Germany, which does not have water scarcity, then that makes sense to do it in that particular country because they can generate the electricity, they can use the water, and they can spray dry with a clear conscience. But if you're spray drying powders here in South Africa that have water scarcity for serious months of the year, it doesn't really make sense for you to put the burden on that particular country. Now, some of you might be jumping to conclusions and saying, well, if there's water scarcity in these countries, should we be having manufacturing in these countries? Should we be asking them to be doing water-intensive exercises like tanning? I argue that you do. You do want to make sure that these countries are doing it. They need the money. They also have the raw materials. Argentina, South Africa, they have a lot of the raw materials that the industry requires. But as long as we don't export water away from those countries, that won't aggravate the scarcity of water that they have there. So if you use the raw materials in there, and it takes about 16,000 litres to grow a cow, if you grow that cow in South Africa, that cost has already been incurred because they need the meat. You then do the water processing, and as long as you try to use water technologies that minimize their use, and you try to minimize the impact of their virtual water, you are going to not aggravate the particular situation that they have. It doesn't make any sense for you to produce the cow there, incur 16,000 litres of water footprint, export it to the UK, process it there, process it back to South Africa, backwards and forwards, because all of that is going to consume fossil fuel, it's going to use more water indirectly, and as a result you're going to obviously have a much bigger water footprint. Now this kind of situation in this graphic that I've shown over here is an excellent tool of allowing global decision making to be able to say, okay, this is where leather manufacturing is taking place. The water footprint is going to be incurred in some way. We need to minimize the amount of water footprint that we have. And so let's think about where the processing is taking place, and let's target the technology that we use there to try and lower their direct water consumption. Of course, I'm simplifying something that gets quite complex, but this kind of measurement ultimately allows decision making at a government or a global level. So, virtual water. When services or goods are sold or moved, the direct water use moves with it. Getting another country to process it for you means that the water is still used and needs to be included in your footprint calculation. It's a way of measuring exactly where the water in the world is moving. And governments progressively are starting to look at the water footprint as a way of setting benchmarks and saying to industries that if you're not conforming to this benchmark, this water footprint, then you shouldn't be doing this processing in this particular country. And so we've got to be looking at this as a tool in our industry as well. All right, so importing finished leather, you still need to include the 25,000 litres that was included in its original manufacture. Even though it was done somewhere else, that becomes your water footprint. It allows identification of manufacturing units or countries that have a water surplus, or an excess, or a deficit. And if you identify this, if you identify these places, then you probably shouldn't make the intensity of their production too high. You try and save water in some way. At the moment, we don't have a lot of data. There is some numbers that appear on the Water Footprint Network, but there's some good papers, in particular the 2016 paper that I showed you is quite good. And if you like YouTube, some good videos out there as well. All right, most of you know what our current treatment options are in terms of wastewater. Either a biological, either a chemical, or a physical method. And of course, I'm going to look at one of the methods that I think is quite useful for some tanneries that are already using them as a useful tool for helping to minimize your water use. Cross-flow filtration has been around for a long time. When I was a student, our laboratory had a look at cross-flow filtration. We were filtering tannery effluents. I also remember when I first arrived here, Christine was working at BLC. We did an STI project where we were looking at using membranes, cross-flow filters. The principle of cross-flow filtration, instead of the filtrate coming through here and getting jammed, blocking all these pores, you kind of circulate the effluents in this direction. The water still goes through, you filter the stuff out, but it doesn't clog up because this flow clears it. Now, we still have a lot of fat in our industry, so these membranes tend to foul up quite a lot, and I think that was one of the findings that we found. But technology has moved a lot on since 2002, and you can get some very good enzymes that can clear these, some good alkaline washing methods. Of course, nanofiltration, reverse osmosis to remove salt, especially with a sustainable energy source. This becomes quite lucrative. You've seen this by the increase in the number of countries around the world that are desalinating. Ultra microfiltration allows you to remove most of the general pollutants, and this leads to closed water systems. My good friend Richard showed me some lovely pictures of some tanneries around the world that are using closed water systems. The only thing that comes into the tannery is the water that they import. Nothing leaves it except the water vapor that comes with the drying or evaporation from the processing throughout the plant. But the rest is all contained in a closed loop, and this allows tanneries in very water-scarce countries to actually export water for the first time. And of course, coupled together with the fact that this tanneries might have a very big roof space, means that they could actually be adding water to their general communities as well. The US has some excellent systems where they're using closed water systems from breweries. Of course, they export the beer, but there are other ways in which they get the water back to be able to claim closed water systems. And I think tanneries could use this to a greater extent. 5 minutes. Recovery and reuse. We all know that we've tried recovery systems and recycling systems. A lot of tanneries have had great success with this. It's always going to be a good option for tanneries to use to try and save water. We know that you're limited with how many cycles you can recycle your sulfide and chromium. We don't have a lot of data on if you are recycling your soak and pickle liquors. We don't know how many cycles you can use it before you have to dispose of it. And then, of course, some of the high exhaustion tanning systems, we know that pretty much most of the chemicals are removed and it's pretty much clean water at the end of it. All right, so some of the modern thinking. Two main functions take place in the drum. First of all, we're going to have the extraction phases, and of course we're going to have penetration phases. I'm not going to bore you with the details, but many of you will know that in some parts of the tanning process we are trying to remove things, other times we're trying to put things in. Now this governs your logic and your thinking if you're trying to take your technology into a modern era. First of all, the extraction. We all know you can't wash things with a little bit of water. So if you're doing an extraction operation, then of course you need lots of water and you need to have some kind of solvent that everything that you're trying to extract wants to be in. Of course, you could use emulsions or special systems that will allow whatever you're trying to dissolve to go into the water. And typical examples will be float length closed door versus open door washers, which may result in time savings. Of course, energy savings. We also know that if you're going to be using a large, big wash, compared to some smaller washes, there might be some advantages as well. And we need a little bit more research into which of these is the better option in terms of the water. Of course, in penetration, we know that the movement of water in is osmosis. We know the chemical movement in. We know that these are dependent on concentration effects, and so that if you have a very large float, you tend to retard diffusion, but obviously drive osmosis. These can be exploited. Mechanical effects, compaction, flexing, ringing, material sensitivity, material breaking, the looseness that you might get, change the amount of float. These are all important things that you need to think about if you're doing a penetration phase. So the technology could be useful if you're trying to, it could be used to improve the penetration. Of course, if your load is very unevenly balanced, you could be getting a lot of strain on your motor, and if anything strains your motor, it's going to change your water footprint because it's going to require more energy. In other industries, they talk about lifters. We talk about drum furniture, shelves and pegs, and this has been one of the biggest developments in water-saving technology. The deep shelf drums, for example. We know that the Froude number is absolutely vital in calculating exactly what speed of drum you should be having. But the Froude number has been cheated by these deep shelves or by using different materials in the drum with your hides because the angle of repose changes. Quickly going to go through angle of repose. Angle of repose is the angle at which the material starts to slump, and you can change this in the drum. And this was measured, first of all, in 1953 by Mitten, and he had some fantastic trigonometric calculations that did this. And of course, things can change the mechanics of your drum by altering the angle of repose. We also have seen water alternatives. This is a patented Eagle Ottawa process from the 50s. Supercritical we've heard about. Isopropanol, veg tanning. Will spoke to us about deep eutectic solvents. Solid state diluents. We've seen some things in the press about taking water out and putting solid things in between. No surprises what that is. But these will be able to alter the amount of water that you have in the drum and will allow better penetration, but maybe not necessarily the extraction. Some of these things will allow better extractions, particularly fats, but they may not allow the extraction of all types of solids, particularly aqueous solids. Finally, I just want to talk about the density of leather. This seems to be quite an important thing in allowing us to understand how to save water in the drum. The density of the water and the leather is quite important because it allows you to decide whether the water is going to be on top or the water is going to be at the bottom. You're also going to get things like buoyancy. If you have low float in the drum, your buoyancy is going to be affected greatly. If you have lots of water in the drum, there will be pockets of water between the hides and the skins. This will allow good transfer of chemicals, so your penetration in some instances will improve. But we need to understand more about this. Right, so in conclusion, it's constantly changing. We seem to be future-proofing ourselves in allowing technologies that are going to allow better, less use of water. For penetration stages in wet processing, the focus is on mechanical and chemical influx. Low float penetration aids non-aqueous systems maybe. There has to be two parts, water affinity and then mass transfer. So if you put something into the water, at some point you want it to leave the water. Tony mentioned in his book, you have to have this interaction. For extraction processes, you may have to have a very large volume of water, which will allow better solubility, better extraction. But at some stage, you're going to have to recycle that water back if you don't want a very large water footprint. So closed-loop water recycling improvements in chemical and biological treatment and effluent treatment plants, deep shelf drums coupled with energy savings. This is a way of improving your water footprint. And then, of course, because leather making is a batch process, it tends to be quite water intensive. If you use more finishing systems that are continuous, for example, you may be able to reduce the amount of water footprint that you have. I'd like to thank Dr. Lama, who's been very useful in giving me some information for this talk, and thank you for listening.